Composite materials are a category of materials, or we can call it as a material system composed of two or more macro constants. And these macro constants are as such that they differ in shape and chemical composition, and they are essentially insoluble in each other. So what is the difference between the composite material and an alloy? Alloy we define as a mixture of two or more metals which are homogeneously mixed, whereas in a composite material we find the macro constituents which are different in shape and they are not completely soluble in each other, or they have to be insoluble in each other. The history of composite materials dates back to the early 20th century. In 1940, fiberglass was first used to reinforce epoxy, and composite materials have a variety of application. We find its application in aerospace industry because a polymer matrix composite which can exhibit a properties as good as a metallic materials can reduce the weight of a aircraft structure. As a result, more load can be carried, and as a result, the fuel efficiency of a aircraft can be reduced, increased. Also, it can be used in a sporting good industry, automotive industry, and home appliances. So this is one of the aircraft which is entirely made up of a graphite epoxy composite, and this is Lear Fan 2100 all composite aircraft. And this Boeing 767, even in Boeing 777, 787 airplanes, the entire wing box is made up of a composite, and these composites include graphite epoxy composites, hybrid graphite and aramid epoxy composites. So as we have defined, here we can find that composite is a multi-phase material with significant proportions of each of the macro constituents. So the composite we classify them as based on the constituent materials. So this constituent material, first constituent material is a matrix which is a continuous phase. It transfers the stress to other phases, protect the phases from the environment, and based on the type of matrix material we can classify the composite material as metal matrix composite, ceramic matrix composite, polymeric matrix composite. Matrix is a continuous phase and it holds the other phase, and this other phase is known as a dispersed phase. This dispersed phase is meant for enhancing the matrix properties. So as we see here, the metal matrix composite yield strength can be increased, tensile strength can be increased, creep resistance can be increased by making use of a proper dispersed phase material, and a fracture toughness of a ceramic matrix composite can be increased. Polymer matrix composites, Young's modulus, yield strength, tensile strength, and creep resistance can be increased. This dispersed phase can be classified as particle, fiber, or structural composite. Okay, here we find a dispersed phase in the form of a fiber in this slide. See, there are different alignments of the fibers. Either there can be in the form of a thin fibers, cylindrical fibers, or a prismatic, and they can be aligned randomly, or they can be aligned in an array, in a horizontal array or a vertical array as shown in this figure. So this is a detailed classification of a composite material. As we have seen that dispersed phase is classified as particle phase, fiber phase, and a structural phase. So based on this, based on the different geometry of the dispersed phase, we can classify the composite material as particle reinforced, fiber reinforced, and a structural reinforced. Particle reinforced consists of a large particle reinforced composite and dispersion strengthened composite. Fiber reinforced consists of continuous and discontinuous fibers, and discontinuous are further classified as aligned reinforced composites, randomly oriented fiber composites, and structural composites are laminates and sandwich panels. Okay, so here we see this is a plot which indicates increase in the toughness of a ceramic matrix composite. The violet line that you find, it is for a unreinforced, and a particulate reinforced is a blue line, aqua blue color line that you curve plot that you find, and a maroon is a particulate reinforced. Maroon is a particulate reinforced, and a fiber reinforced is a aqua blue. And this is a plot, Ashby plot for PMC ceramics exhibiting their different material properties, and for the MMCs of different aluminium composition with different reinforcement in the form of a whiskers. We can see the properties and the benefits of using composite materials. Okay, best example of a particulate reinforced composite is a spheroid steel, which consists of a matrix of alpha ferrite. In that we find a cementite as a brittle cementite as a reinforcement. Tungsten carbide and cobalt is also an example of a particulate composite. In the automobile tires, we find the nanocarbon in the rubber, which increases the tensile strength and wear resistance of the natural rubber. So, nanocarbon that we make use of in the automobile tires is a particulate reinforcement. Concrete is also an example of a particulate reinforcement. And fiber reinforced fiberglass that we make use for automotive application. And this is a kind of loading that we find, load distribution that you find in a typical composite material. When stress is applied, matrix takes away the load from the fiber, and the fiber dissipates the stress within the matrix. Okay, so fiber length plays an important role. So is the critical fiber length we define for effective stiffening and strengthening. So fiber length, if it is greater than 15 times the fiber strength in tension multiplied by the fiber diameter divided by the shear strength of the fiber matrix interface, that length we call it as a critical fiber length. For fiberglass, fiber length should be greater than 15 mm, and if it is less than 15 mm, then shorter thicker fiber we call them as, and longer thicker fiber, it should be greater than 15 times the sigma FD divided by the shear strength of the fiber matrix. This is a load distribution that you find for a critical loading. Fiber materials can be whiskers in the form of graphite, silicon nitride, silicon carbide, and they exhibit high crystalline perfection, as a result extremely strong, strongest known, very expensive. Fibers can be polycrystalline or amorphous, generally polymers or ceramics of alumina, aramid, E-glass, boron, ultra-high molecular weight polyethylene. Wires can also be used. So the fibers can be classified as whiskers, fibers and wires. So this is the direction in which the fibers can be arranged, aligned continuously, aligned discontinuously and randomly dispersed. This is the load behavior of a fiber reinforced composite, and this is the stress distribution that we find. And these are the few of the equations that we find for a composite material. Okay. Okay, structural composites. What are the structural components? These are stacked and bordered fiber reinforced sheets stacked in a sequence based on the required orientation. As a result, they are balanced. We get a in plane stiffness. Sandwich panels are low density honeycomb structures cores